Our Sun, a blazing sphere of plasma at the heart of our solar system, is not as tranquil as it appears. It is a seething cauldron of activity, capable of unleashing bursts of energy that dwarf anything we can create on Earth. These outbursts, known as solar flares, are a stark reminder of the raw power of our nearest star and its potential impact on our technological civilization. Solar flares occur when magnetic energy stored in the Sun's atmosphere is suddenly released. This energy bursts forth as a flash of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. These eruptions can last for minutes to hours, bathing the solar system in a torrent of high-energy particles. The intensity of these flares is categorized according to their X-ray output. The most powerful X-class flares can disrupt radio communications, interfere with GPS navigation, and even damage satellites in orbit around Earth. These events, while awe-inspiring in their power, highlight the importance of understanding and predicting solar activity to protect our increasingly technology-dependent world. Sunspots, dark, cooler regions on the Sun's surface, serve as visible markers of intense magnetic activity. These regions, often larger than Earth itself, are associated with solar flares and other eruptions. One such sunspot, designated AR 3697, emerged in late 2023 and quickly gained the attention of solar scientists. AR 3697 was notable for its size and complexity, harboring a tangled web of magnetic field lines that stored vast amounts of energy. Observations from space-based telescopes revealed frequent flares erupting from this region, sending streams of charged particles hurtling through space. These observations raised concerns among scientists about the potential for a significant geomagnetic storm if a large flare from AR 3697 were to strike Earth directly. Geomagnetic storms, caused by the interaction of the Sun's charged particles with Earth's magnetic field, can disrupt power grids, damage satellites, and pose risks to astronauts in space. As AR 3697 rotated towards Earth, scientists closely monitored its activity, using sophisticated computer models to predict the likelihood and potential impact of any Earth-directed eruptions. Their observations and predictions underscored the importance of space weather forecasting in mitigating the risks posed by these solar events. When a coronal mass ejection, or CME, a massive burst of plasma and magnetic field from the Sun, slams into Earth's magnetic field, it triggers a geomagnetic storm. This interaction compresses Earth's magnetic field on the sunward side and stretches it out on the night side, creating a geomagnetic tail that extends far into space. As the CME's charged particles interact with Earth's magnetic field, they generate powerful electric currents in the upper atmosphere. These currents flow along Earth's magnetic field lines, inducing fluctuations in power grids, disrupting radio communications, and heating the upper atmosphere. The severity of a geomagnetic storm is classified by the intensity of the disturbance in Earth's magnetic field. Minor storms may only cause minor fluctuations in power grids and auroral displays at higher latitudes, while major storms can cause widespread blackouts, damage transformers, and disrupt satellite operations. The impact of geomagnetic storms highlights the interconnectedness of Earth and space weather. Understanding and predicting these events is crucial for protecting our technological infrastructure and ensuring the safety of astronauts in space. One of the most spectacular and well-known effects of geomagnetic storms is the aurora borealis, or northern lights. This mesmerizing display of shimmering curtains of green, blue, and red light dancing across the night sky captivates observers and has inspired myths and legends for centuries. The aurora is caused by the interaction of charged particles from the Sun with atoms in Earth's upper atmosphere. These particles, channeled by Earth's magnetic field towards the polar regions, collide with oxygen and nitrogen atoms, exciting them to higher energy levels. As these excited atoms return to their ground state, they emit light at specific wavelengths, producing the characteristic colors of the aurora. While the aurora is a beautiful and harmless phenomenon at high altitudes, the intense currents flowing in the upper atmosphere during a geomagnetic storm can induce electric currents in long conductors on the ground, such as power lines and pipelines. These induced currents can overload power grids, causing blackouts and damaging transformers. The 1989 Quebec blackout, which left millions of people without power for hours, is a stark reminder of the potential impact of geomagnetic storms on power grids. As our reliance on electricity grows, so too does our vulnerability to these events. In 1859, the most powerful geomagnetic storm ever recorded, known as the Carrington Event, struck Earth. This event, caused by a massive solar flare, disrupted telegraph systems worldwide, sparking fires and causing widespread auroral displays visible even in the tropics. At the time, the world was far less reliant on electricity than it is today. However, the Carrington Event serves as a stark reminder of the potential consequences of a major geomagnetic storm on our modern technological civilization. If a Carrington-scale event were to occur today, the impact on our power grids, communications systems, and satellite networks would be catastrophic. Widespread blackouts could last for weeks or even months, crippling transportation, healthcare, and other essential services. The Carrington Event highlights the importance of understanding the risks posed by extreme space weather events and taking steps to mitigate their potential impact. Investing in resilient infrastructure, developing accurate space weather forecasting capabilities, and raising public awareness are all crucial aspects of preparing for the next big solar storm. Just as we monitor and forecast terrestrial weather to prepare for hurricanes, tornadoes, and other natural disasters, predicting space weather is becoming increasingly important for protecting our technological society from the wrath of the sun. Space weather forecasting involves monitoring the sun's activity using ground-based observatories and space-based telescopes, analyzing data on solar flares, CMEs, and other solar phenomena, and using sophisticated computer models to predict their potential impact on Earth. By providing timely and accurate space weather forecasts, scientists aim to give governments, power grid operators, satellite operators, and other stakeholders time to take preventative measures to minimize the impact of geomagnetic storms. These measures might include temporarily reducing power grid loads, adjusting satellite orbits to avoid the brunt of a solar storm, or delaying spacewalks to protect astronauts from harmful radiation. Accurate space weather forecasting is crucial for mitigating the risks posed by the sun's unpredictable outbursts. As our reliance on technology continues to grow, so too does our vulnerability to the impacts of space weather. Mitigating these impacts requires a multi-pronged approach that involves hardening our infrastructure, developing backup systems, and raising public awareness about the risks of space weather. One key aspect of mitigation is hardening critical infrastructure, such as power grids, to withstand the effects of geomagnetic storms. This can involve installing surge protectors, adding redundancy to the grid, and developing new technologies that are less susceptible to geomagnetically induced currents. Another important measure is developing backup systems for critical communications and navigation systems that could be affected by space weather. This might involve deploying ground-based navigation systems that can operate independently of GPS satellites, or establishing alternative communication networks that are not reliant on vulnerable satellites. Raising public awareness about space weather and its potential impacts is also crucial. Educating the public about the risks, providing guidance on how to prepare for space weather events, and promoting responsible use of technology during periods of heightened solar activity can help minimize disruptions and ensure public safety. Studying the sun and its behavior is essential not only for understanding the risks of space weather, but also for unraveling fundamental mysteries about the universe we live in. The sun is our closest star, providing a unique laboratory for studying the physics of stars and the processes that drive their evolution. By observing the sun's magnetic field, its internal structure, and the processes that drive solar flares and CMEs, scientists can gain insights into the fundamental forces that govern the cosmos. These insights have applications in fields ranging from astrophysics and plasma physics to energy production and materials science. Moreover, understanding the sun's long-term variability and its impact on Earth's climate is crucial for addressing the challenges of climate change. By studying past variations in solar activity and their correlation with Earth's climate, scientists can improve climate models and develop more accurate projections of future climate trends. Investing in solar physics research, developing new new observational tools, and fostering international collaboration are all essential for advancing our understanding of the Sun and its impact on our world. The Sun, the life-giver of our planet, is also a source of potential hazard. Its unpredictable outbursts, like the solar flares that emanated from Sunspot AR 3697, remind us of the immense power of our nearest star and the importance of understanding and respecting its influence on our world. As our technological civilization becomes increasingly reliant on space-based assets and interconnected power grids, the risks posed by space weather will only continue to grow. Investing in space weather forecasting, hardening our infrastructure, and raising public awareness are all crucial steps in mitigating these risks and ensuring the resilience of our technological society. By unlocking the secrets of the Sun's behavior, we not only protect ourselves from its fury, but also gain a deeper appreciation for the intricate workings of the universe we inhabit. Our future on this planet is inextricably linked to the Sun, and understanding its every whim is paramount to our continued prosperity and survival.